Now we'll see how these functions can be implemented. Okay, so we have consider this program. So if you see this call, this is a new instruction similarly written. So using call and return instructions we can implement function. Okay, how we will see. So how this call and return can be implemented is there are so many ways. I am talking about a particular implementation. So depends on the machine architecture, it varies. But one idea is by maintaining one link register, which is a dedicated register which is going to remember the, so I can say the next instruction to be executed. We'll see the usage of this link register. Example, what you want to do is you want to execute your normal instruction. Suddenly you want to go to a method called sum, right? So sum is here to here. Okay. After that you have to come back to, you want to come back to, normal execution again. That means you want to come back to store. So the same thing I have explained here with memory addresses. Example, let's say your program is loaded here. Initially your program counter is showing 100. Such a way we planned it. Then later it will go to 104, 108. But whenever there is a call, then after 108 we should not go to 112, right? We have to go to from 108 to 116 because the sum routine is implemented here, otherwise loaded here, right? So after completing 120 instruction written, then we should come back to 112. So how that can be done? For that, do we have machine support? Yes. Generally, the architecture people give you support through this kind of instructions. So like call and return. Typically, the more or less the functionality will be same. That's why you understand this idea so that you can understand the ideas depends on, exact ideas depends on the architecture. Example, let's say you want to know how Intel people implement this call and return. For that you have to go through their machine instruction set, right? So it varies from one machine to another machine, but the core idea is same that we should understand. One of the way we'll try to understand now. One way how we can implement is maintaining one link register. Now what we do is we blindly execute our program like normal program. So initially program counter will be 100. So load R1 comma A. So when it is executed, what happens? So I'll show here. R1 contains now value of A, correct? What is value of A? What is value of A is 3, right? Now next instruction we know that, right? R2 quite common, which is 4. Then next call. Whenever call instruction is executed, I will tell you the functionality. So automatically we will go to the the label directly, the memory address where this label is mentioned. Okay, example, sum is mentioning that go to 116, correct? So because of call instruction, what happens is step number 1, we go to address, starting address, I can say start address where the method is loaded, correct? Where the method is loaded. Second step is, so before going there, so we have to store the return address into link register. Okay, so what is the link register here? Let's say this is a link register. In that link register we are going to return. After 108 we have to come back to 112, right? But how your processor knows that exactly it is 112? Simple. So already program counter at that time when we are executing call, it is 18, correct? But when you are executing this call, part of that we know that program counter will be incremented generally, correct? Then it will become 112. So try to understand, it is already 18 when you started executing call, but already I told you while executing any instruction, while in the execution phase at some point of time we increment program counter. Assume that already program counter got incremented. Let's say then only, it's all about implementation. So then only, so that incremented value will be stored here. Such a way we can plan call instruction. Now executing call instruction is nothing but going to sum. So directly sum, you see I am writing an assembly level program, but in the machine level program sum will be clearly 116. If you have an instruction like call 116, is it a big deal to go to 116? Not a big deal. For that only one thing we have to do is we have to write 116. Here V means the instruction execution should do that, correct? So in the, because of that instruction execution, automatically program counter will be updated with 116, link register will be updated with 112. This entire thing is functionality of call instruction. Looks little bit lengthier, right? Yes, but only two things. You see, this link register should be updated. That's why better we will have this in register. Okay, so that it will be quick rather than memory. Second, program counter has to be updated. Only two updations, especially they are register updations, not a big deal. Then after that, what? Complete. Come on. So after this call instruction, we'll come here, right? Because program counter says that 116. Then blindly this line will be executed. Add R3, R1, R2. Now here you can understand one thing. So R1, R2, we are writing this code means what? Then maybe you know that R1 and R2 contains parameters. So here this R1 comma R2 can be treated as parameters, right? So finally we are getting an effect of passing the parameters also. So parameters are 3 comma 4 for me. Then I am adding them into, adding them and I am storing it into R3. Then R3 gets what? 7. So in that way, by carefully planning it, then we can get the sum and after that return, right? So now this program and this program knows, like, what are the, this sum knows that R1 and R2 are parameters for that method, and this method knows that R3 is nothing but the return value. Okay, in that way we can feel. Okay, not a problem. Now here see, once this line is done, then execution comes to return, right? Now how return can be executed? That means what is the functionality of return you should know, because it's a new instruction. Other instructions you know, right? Sir, what is the meaning of return? Simple. Whenever this return is executed by your processor, the processor control circuit will be such a way that it will automatically will go to link register. When it goes to link register, that is 112, that will be blindly copied into program counter. That is what the meaning or execution of this return. So that means now once you execute this return statement, then we have to execute another instruction that is pointed by program counter. Program counter is pointing now 112. Automatically this store instruction will be executed. So R3 comma C, right? Store R3 comma C. This R3 will be stored into C. Then we store here in that way. So R3 can behave like a return value. Correct. R1 and R2 can be given as parameters. In that way, when you write a high level program, your compiler can convert that to this kind of low level instructions, right? Finally, we can simulate function execution, right? But we have two extra instructions which we learn now, call and return. But there is a danger, you know that. What is the danger is when a function calls another function, that is called nested function, right? So nested function calls. What happens, sir? We will see. Example, let's say you have link register. Now let's forget about this coding and everything. You understand now, right? So we can implement functions, but only problem is how this method works when you have multiple function calls. That means a function, in a function again you have another function. Example, let's say you are executing instructions at 100, after that 104, after that 108, but 108, instruction at 108 memory address is like here a function call. Okay, because of that call we are going to 500, such a way it is designed. Then after that we have to come back to 112. This is normal execution. Then if you go to memory address 500, there is an instruction after that normal instruction, then 504, 508, in that way. Again there is a 512, then suddenly there is again a function call. Okay, let's say that call is going to 700. Then from 700 to let's say 708, 712, this is the way this execution is taking place. Now you see one thing. The difference between this one and this one is you have multiple function calls in a call. Because of this call you went here, because of another call again you are going to another place, right? Now we will see blindly what is going to happen if you blindly execute that implementation. That means we have only one link register. So what, sir? You see? So in the link register, first of all we execute 100, right? You have program counter. Program counter is initially 100. Then that will become 104. Then that will become 108. So when it becomes 108, there is a call. Because of call, so we have to go to 500, but by that time, so the next instructions address, that means 112 will be stored in link register. Okay, we do that. Then we directly update program counter to 500, correct? Yes, perfect. Now after that we execute it. Then program counter will be, because of this execution of this instruction, 500 will become 504, 504 will become 508. 508 will become 512. Suddenly there is a call, right? So when you execute this call instruction, first of all, so program, we know that in this, because of this instruction also program counter will be normally updated. Okay, 516. but still call is not completely done. Now what we have to do, this 516, because of part of call instruction there are two things. What is the meaning of execution of call instruction? The next program counter value, which is 516, correct or not? So the next is 516, that should be stored in link register. Sir, that means we are losing 112. Then I ask one question, why do you want 112? Because sir, we have to, once we will come back to 512, 516. After that we have to go to 112, and that instruction address is important for us, right? But if you have only one link register like this, so that is going to happen, right? So for that we have a stack pointer. We'll see how to implement this stack pointer. So like program counter, stack pointer is a register. Okay. Now we are going to implement a stack called processor stack. Okay. So assume that we can implement processor stack. So that processor stack is going to help you, doing this stuff. What is that? Implementing nested subroutines. So this processor stack, of course, it's like a, data structure stack. You know the functionality of stack, right? Now example, currently this stack we are implementing in memory somewhere from bottom to top. So these locations are given for us. Okay. Now assume that this is 100, this is 104, 108, like this, 112, so on. Now currently let's say stack pointer points to 96. So I would like to add some data here, some value here, okay, whatever it is. So how you write it? What is the code for that? That is called push, right? So what is the code for push? What is the code for pop? We'll see. For push, of course, because it is from bottom to top, the instruction values will be like this, right? Maybe this is 100, this is 96, this is 92, this is 88, in that way, right? 84, so on. That means whenever value is decreased, then you are going to push, correct? So initially it will be 104. Now step number 1, if I want to write data here, what should be the operation? So stack pointer should be decremented, correct? The code for push is stack pointer equal to stack pointer minus 4. So in assembly level, what is that instruction? Directly add stack pointer and hash 4, correct? It's not addition because we have to decrement the value, subtraction. So this is the code we can use for pushing. Now what is the popping code? How to pop? Example, when you want to pop, then we have to take the data. Once you take the data, yes, we can take the data, right? How to take the data? Maybe if you want to take the data into some register, so we can do like this. Load the data top of the stack into register R1. And what is how to take that data? Simple. Go to stack pointer, there will be a memory address, and go there, you get the top of the stack. Once you take it, then we have to decrement the stack pointer. Sorry, we have to increment the stack pointer. How to do that? For that we have to use an instruction called add stack pointer hash 4, correct? In that way we can increment and decrement stack pointer, and we can implement pop and push operations, correct? So it's not a big deal, you can understand that. So this is called a concept called processor stack. Assume that we have a processor stack and you are ready to push an element, otherwise pop an element. Now how these nested calls can be implemented, we will see. Now you remember, you have to do this this is as a part of your code, okay? So now we are not going to get the machine support, you have only stack pointer. Using that, in your code we have to implement it, okay? Now remember it, we have only two things. So there is a link register now already, correct? Assume that, let's say that link register can be accessed. Let us use a name called LR, link register, okay? Now, so in this link, I don't write the code, but we have to remember one thing. Finally, to implement nested calls, generally, we have to write sophisticated code, assembly level code. But we can do it. How you see? Assume that link register can be accessed. I will tell you the technique, but I don't show the code because it will become very lengthy. Okay? Remember, sir, how to implement that code? Please at least give us idea. I'm going to give the idea. Now we'll see how to add extra functionality so that nested calls can be supported. For that we are going to add extra code. Remember that. As a assembly programmer, we should do that. We have now call and return support. So there is a call method. Already you know how call instruction works, and you know how return instruction works, right? Now forget about your code. If you don't write extra code, what is going to happen? We'll see one more time. so that you get clear picture now. So initially, let's say you are not using stack, blindly you are executing your program 100, 104, 108. Recall what is call instructions functionality. Because of call instruction, then link register will be getting 112 because next instruction, that is program counter's value, then program counter, and I have forgotten to show you program counter. So program counter will be loaded with that call address. What is that? 500. So happily program counter comes to here 500 and it will start executing these instructions 500, 504, 598, 512, so on, right? Then suddenly there is a call method again, right? Call method 2. So it is at 800. Okay. So because of call, so I want to tell you that here there is a call which is going to 800. Like here call which is going to 500, right? So now 8 because of 800 will come here. Recall. Whenever there is a call, what is that call instructions execution says? Simply because of call instruction execution, then link register will go to what? Return address. After 800, after 512 we should go to where? 516, correct? This is the return address. Here it is. Now change it to 516. Now blindly go to 800 and execute 804, 805. Then return. Because of return, what happens? We have to come to 516, right? So when you come to 516, then we can complete this method's remaining instructions. Perfect. Then at 520 there is a return. Recall what return does. Whenever there is a return, it will go to link register and it will show 516 again. But if you go to 516, then you come back and there is an infinite loop, because this is not a proper design, correct? So finally what I would like to tell you is, if only this kind of call and return methods are given, return instructions are given, and if you don't use them properly, then nested calls cannot be implemented, but single call will be implemented, correct? So then how to enhance it? That is your job now as an assembly programmer. So what we can do is, I will tell you, if you have a stack pointer, we can achieve it. How to get the nested calls, we will see. What I do is, so here whenever there is a method call, whenever there is a call, so blindly I will go to that call and I update. I'll show all the values. Initially program counter is at 108 now, correct? Now, and when call is executed, program counter becomes 112, correct? Now it is a function call, call instruction. We have to go to 500. Then program counter will be updated to 112. But before that, link register will be given that 112. Then after that, program counter will be updated to 500. You know the remaining story, same story, right? Then 500, 504, 508, everything good. Now here I would like to tell you one thing. The person who has designed this method 1, he should be careful and he should do extra stuff. What is that, sir? Because he is writing one more call, right? Because of this call, the link register will be damaged. But that should not happen. That's why. So before this call, wherever, here, so some extra functionality should be added that I am not directly showing you, but I will tell you the result. Because of that, what should happen is, this link register value should be pushed into the stack. Yes, already I told you how to use stack pointer, correct? Using stack pointer we can push it, not a problem. Simply do one thing. SP equal to SP minus 4, 24 equal to 24 minus 4, 20. Such a instruction we can write it. After that, access this link register. Now assume that we have access to link register. Then access that link register. Recall, what was that? 112, right? So here 112. So push 112 here. Perfect. Then continue as usual. So when I continue as usual, then what happens? We will go to call 800. Okay. Because of call 800, recall, what happens? This link register will be damaged to, modified to what? 516. Sir, is it okay? Yes, we saved it already. That's why there is no problem. Now you see, when you go to method 2 and when we come back return, when we return, then what is going to happen? We will be getting 516, correct? Then we can happily come back. But remember one thing, because of our call, we spoiled this link register, right? Then once we go and come back, we have to add some more extra functionality. What is that? I will tell you. Let us not do any functionality. Blindly execute this program. What happens? We'll see. So because of this return, where to return? 516. See the link register 516. Then execute. Then again there is a return at 520. What to do? take y16 again. Do I need to take y16 again? No, this time I have to take 112. For that, what we have to do is, once this call is done, here some extra functionality we have to add. I show here. Okay, this is, let's say, your 512, where this is your return, which is nothing but something 520 whatever. Here you have to add extra functionality. Sir, what is that extra functionality? That should do popping back this stack. That means 5 to 112 should be popped, and again here it should be kept. Can I write such instructions? Not a big deal, right? It's after all moving memory to register. Yes, I did it lot of times, correct? So if I do that, what happens, we'll see. Then once you come back, happily you execute your normal program. Because of extra functionality 112 is added here, then 520 comes at return. Whenever there is a return, recall. What is the meaning of return? Going to link register. That is the way return is designed. Go to link register, take the value. What is that? 112. Because of that, control goes, so that will be updated in program counter. Of course, I am not showing program counter properly, but now I am showing. It will go to 112. Then we'll execute the normal one. Is it not the right thing? You see, we started here, first 100, 104, 108. Because of call, we went here. Then because of this call, we went here. Then we came back. Did you remember? After that, we should go back to 112. So that will happen, right? In that way, we have to add extra functionality here, extra functionality. This is for pushing the link register into the stack. This is to popping the link register. In that way, if, sir, what about this method 2? If method 2 has another call, yes, if this method 2 has another call, we should repeat this process again when there is a method, another call, let's say. Okay, let's show that. At 808, there is a call like this, call to 2000. Then what you have to do is, here the extra functionality should push. Example, we were pushing 112, right, into stack. Then 516 also should be pushed by this extra functionality, and 516 should be powered by this extra functionality. Such a way we have to implement. See, if you understand here the concept, same thing if you can repeat, right, not a problem in that way. So stack pointers can be used to implement nested functions. Okay, that is one thing, and of course we can use for other purpose also, right? So this is the story about stack and nested functions. And remember one thing, of course I did not discuss, but the arguments also generally we push. Okay, did you remember in data structures algorithms I taught, whenever there is a function call, generally we push all the arguments into the stack, right? Same story here also, same thing we do. Okay, so remember one thing, however, whatever the way you are pushing these return addresses, along with that all the arguments also we push. Okay, that part you just think about it. Okay, in that way, so we can implement nested functionality, and also we can push the arguments also, right? In that way perfectly we can implement it. So this is all about, you know, machine instructions, and what is another thing, so addressing modes. But perfectly we learned all the addressing modes and all the functionality. If you know whatever, if you attend my lectures up to this point, then you can answer any gate question. Okay, but you should have patience. If you want to answer difficult questions, then you should understand difficult concepts. When you try to understand difficult concepts, definitely your brain will become heat, right? And that you should go through that. Otherwise, if everything is simple, then everyone will get first rank. That point you should understand. But how to get a better rank? For that, definitely you should work better than others. For that, we have to put lot of effort. Okay, for that we have to understand lot of details. Okay, so you should understand lot of this kind of difficult functionalities and everything, so that any gate question you can answer.